Hey, I've been out looking for functions for you. Hey, I've got a whole lot here, and I've also got a puzzle. Look at the heading of this presentation, the product and quotient rules, and the puzzle I've got goes like this. There are some red functions and some blue functions. Is there anything different about the blue functions from the red functions in terms of finding the derivative? The product and quotient rules are rules for finding the derivative or the slope of the tangent of point for any product or quotient function. So I'll give you a little bit of time now. You want to pause the presentation. What's the difference between the blue functions and the red functions? Alright, let's look at the answer. I wonder if you got it. All the blue functions, there's one, and there's another, two products. There's also a quotient. I hope you remember, a quotient is a term belonging to the division process. When you're dividing two expressions, a quotient is a number of times it goes in, doesn't it? So that's where the quotient rule comes from. And this one here is a quotient. What did you notice about all the blueies? Well, you could actually already get the derivative of those, couldn't you? You could expand this. That by that, all this expansion here, and then use x to the n rule. Okay, for that one. Over here you could do the same thing. Down here you could expand it, divide through by x cubed using subtraction of powers, and again x to the n rule. You could already actually do these. Could you do this one? Yes, you could divide each term in the top line by x, and again, x to the n rule. However, let's have a look at some of the red products in quotients. You can't actually expand this. The root of x plus 1 is not root x plus root 1. Okay, so you can't break that down and expand it. Similarly here, okay, sine squared x by x squared plus 2. You could say that sine squared x by x squared plus 2 sine squared x, but you still have a product in there. What about this one? Can you divide x squared plus 1 into x squared plus 2x take 3? No, you can't, and you therefore can't use x to the n rule. Can you see that you're not allowed to split the denominator? This is not x squared plus 2x take 3, divide by x squared, and then divide by 1. What this statement in the bottom line says, this x squared plus 1, is it's x squared over x squared plus 1, plus 2x over x squared plus 1, take 3 over x squared plus 1. Every term in the top line must be divided by the whole of x squared plus 1. So you can't split a denominator. Okay, what about this one over here? This is a quotient, and you can't divide it out either. So can you see that we do need a rule to cover products which aren't expandable and quotients which aren't divisible directly back to an x to the n form? There's our problem. Let's get on with it. I hope you spotted that difference, that you could already do the derivative of the blue ones but not the red ones. Alright, let's go down and have a look at the product rule. Now in this course, it's not part of the course for you to know the proof of this one. But what I'm going to do is to show you how it works basically. So if we've got two functions, u of x by v of x. Now this screen clipping comes from Pearson's. I will be, from Hayes and Harris. I will be using some from Pearson's as well. And we'll look also at what the IB information booklet or the formula booklet gives us to help us in exams. Okay, so there's the two functions, u of x by v of x. What do? You get the derivative of the first times the second function unchanged, plus the first function unchanged by derivative of the second. Or you could do it in du by dx notation down here. Okay, you could do that. So, it's disappointing, isn't it? I guess you would have hoped that the derivative was what? Just the derivative of the first by the derivative of the second? Haha. No, bad luck, mate. No, not that easy. It's all this stuff here. Let's check it out using an x to the n approach and just verify, this is not a proof, but verify for a pair of functions that this product rule works. So let's have a look. let's call f of x equals what? X plus 1 squared by, let's say, x plus 2. Now, we don't have to use the product rule for this because we can expand it. So let's expand it and see what it is using the x to the n rule. This first bracket is x squared plus 2x plus 1. A perfect square, a plus b all squared, is a squared plus b squared plus 2ab. Now let's expand it. So do each of these expansions. That's x cubed plus 2x squared plus x, and then through by 2x squared plus 4x plus 2. So we're getting there down to x to the n's, collecting x squared terms. There we have our expanded function. Oops, that's not f dash x yet, I haven't differentiated, I've just expanded it. So now f dash x will be 3x squared plus 8x plus 5. Fair bit of work there. So what we want to try and do rather than that expansion is to come up here to the rule and apply it. Let's have a look. If f of x equals x plus 1 squared by x plus 2, this is our u function, if you like, and this is our second factor, our v function. So according to the rule, what does u dash v mean? Got to find the derivative of this. So it's 2 by x plus 1 to the 1. This is a function of functional chain rule, times the derivative of what's in there is 1, so that's u dashed of x. Then we put v unchanged, then plus u unchanged by the derivative of v, which is derivative of x plus 2, which is just derivative of x, which is 1. Derivative of 2 is 0. So let's keep going now. Let's put the 2 out the front, multiplying these two together. We've got x squared plus 3x plus 2 plus, bracket, let's expand this, x squared plus 2x plus 1. So here we are, 2x squared plus 6x plus 4 plus x squared plus 2x plus 1. So this is, what, 3x squared plus 8x plus 5, which checks with the x to the n approach. Okay, do you get it? Okay, so it's not ideal, a fairly complicated arrangement of the derivatives. So thinking, come up here to this line again, thinking here what? Derivative of the first times second function unchanged plus first function unchanged times derivative of the second. So mismatch or whatever. Anyway, okay, so this idea of interpreting mathematical formulae, which are generic, right? This is a lot of this works with the whole family or genus of functions, which are products. It's a generic formula. It is often very, very useful to think of it in words. Don't be basing your knowledge just in u and v. U and v represent a whole family of possible functions there. Okay, let's go down and see if we can do some practice on this. Alright, example 7, this time from Pearson's. Use the product rule to compute the derivative here. Okay, so let's have a look. What you could do is expand it, and then the derivative would be that. They're doing one like I've just done then. But you could think of it as a product of two different terms. So the derivative is the derivative of the product. Now they've got it differently here. They've gone to what the formula book's got. Now there's a reason why you wouldn't do it this way. It doesn't matter. It's still the same combo, isn't it? First unchanged by the derivative of the second, and then a derivative of the first by the second unchanged. It's just that it is valuable to actually think of that in a different order because we're going to be doing a quotient rule shortly, and they look similar if you do it in that other order. That is, the first one unchanged. So let's do that. Well, let's just follow through this example for the moment. So we're leaving the first one unchanged. Derivative of the second up here is 2, and then the second one unchanged, and the derivative of the first, which is u of x, which is 2x plus 3. Then when we expand it, it checks. So they've done one like the one I did up above there. Now generally, you do whatever's quickest. The simplest mathematical solution to a problem is generally deemed to be the shortest. Okay, the shortest is generally deemed to be the most practical or neat or efficient way of solving the problem. So there's not much in it here, is there, if you want to go back to x to the n form. Okay, well, this actually might be a little bit quicker to just expand it. All right, we're going to have to make those choices later on. Let's go on and have a look at example 8 here. Here's a product, x squared by sine x. So we're identifying our two functions. Spot the functions again, that's important. So here they've gone to f and g notation. Function notation form. You can use that, that's good too. Remember, in the information booklet or the formula book that's given in exams, it is done in u's and v's. But it doesn't matter, it should be flexible. So here it is in their pattern again. You leave one unchanged, the derivative of the other, plus the other one unchanged, derivative of the first. Remember, I like to think of this as derivative of the first by the second unchanged plus the first unchanged by the derivative of the second. You'll see why as we go to the quotient rule, because they're very similar if you match them in this way. Okay, so original function is x squared, derivative of sine is cos, and then the other term, sine unchanged, and derivative of x squared is 2x. So you've got to do this combo, this matching up of stuff, and then of course generally we would put 2x in front of the sine x term. Okay, because we're not finding the sine of a product here, so we don't want any of that confusion in there. Alright, are you getting the hang of it? Let's go down. Here's another little screen clipping from Pearson's, talking about the first factor or the first function and the second function. And therefore it's the first unchanged by derivative of the second, second unchanged by derivative of the first. Better to think of this one, I'm going to keep at you, f dash x, first one done, second one left, then first one left, do the second one. And remember, first differentiated, first derivative, second unchanged, and then first unchanged times derivative of the second. That pairing up. Okay, just reinforcing that there. Okay, let's go down. Have a look at a few examples here. Find the exact coordinates of any stationary points and any inflection points for the curve y equals x e to the x. So we're bringing things together now, giving a function where you'll have to use this rule and remembering the stationary points, maximum, minimum, etc. Let's have a look. So stationary points is when the first derivative is 0. And inflection points when the second derivative is 0. So we've got a bit of work to do. Let's do the derivative of this product. Okay, so if we do the derivative of the product, first term, derivative of the second, plus first term unchanged, derivative of, I think I've said that the wrong way there, what have we got? First unchanged, derivative of the second, and then derivative of the first and the second unchanged. Alright, so here, what have we got? The derivative of e to the x is itself, derivative of x is 1, so it just becomes e to the x times 1. So we can actually factorise that, and then that derivative is 0 when e to the x is 0, so here you should say e to the x is not 0. Okay, this product is 0 when that's 0, which is not possible, make that statement, or when this is 0, so that's when x equals neg 1. I like students to actually put in or note that the other factor cannot be equal to naught. Just remembering, e is greater than 1. It's approximately 2.718, isn't it? So when you are raising that to any power, it cannot be 0, cannot also be negative. Okay, so just keep that in mind from your exponential work. Okay, so now let's have a look. We want the coordinates to stationary points, so when x is neg1, sub it back into the function y equals x e to the neg x. So neg1 by that gives us neg1 on e. So it's got a stationary point at neg1 on e. Now we need to know whether that's a maximum or a minimum, and we also want to know points of inflection. So let's go and get the second derivative, which is the derivative of that derivative we've just found. So it's a derivative of the first term plus derivative of the second, and we go through the product rule for the first one, and then derivative of e to the x is just itself. So adding those up, we've got that. Factorising out the e to the x by x plus 2, the derivative is 0 when x is neg 2. Okay. Remembering that e to the x cannot be 0. Okay, so an inflection point will occur at x equals neg 2 if the sign changes at that point. So let's look at the sign diagram of d2y by dx squared. So where we are, and we're going to look at it at x's neg 3 and 0. So we haven't actually got a number line here. I think it's worthwhile doing that. So it's 0 at neg 2. This is a sign diagram for the second derivative. So at neg 3 over here, subbing it in, here it is here, neg 3, get neg 1 over e cubed, which is negative, and then over here sub in 0, neg 3 from there, 0 from there. We have 0 plus 2 is 2, so it's positive. So it actually does change sign there, and so it is a point of inflection where it's changing concavity from concave up to concave down. Okay. So we might be able to use that to tell whether it's a maximum or minimum at our other point. We'll have a look at that in a minute. But we can see there's a sign change, so there is a point of inflection here. So sub in neg 2 into the function, get neg 2 over e squared. So there it is there. We've got an inflection point. And now, because we've got the second derivative, we can use the second derivative test to classify this stationary point, because we don't know whether it's maximum or min. You could use a sign diagram for the derivative, but let's just use the x value here and sub it into the second derivative, and it's greater than 0. So therefore it's a minimum. It's concave up, as I said before, and it's a minimum point for the curve. Just remember that if it's concave like that, the first derivative is negative 0 positive through there, and therefore it is increasing, and therefore it's actually greater than 0. So at a local minimum, the second derivative is positive. And if it was concave down like this, the first derivative tangents there would be positive, 0, negative. That would mean the first derivative was decreasing, so this would be, its rate measurer, rate of change measurer, would be negative. Just remembering that. So the second derivative can be used to tell whether it's a local max or a local min. And therefore we've used that here. Just instead of the sign diagram. You could have used the sign diagram as well. Alright. And here Pearsons have gone and used the TI to just verify those points here. Verify that you have a local min and a change of curvature there. So here, there's your local min, and in here can you see slightly concave to concave down to concave up there. As we go along, you can't see it all that well, but it's in there. Okay, starting to build into bigger functions now that we've got our product rule. What about dealing with quotients that can't be simplified? Okay, if you can't divide them out and use x to the n rule. So here we are, we've got two functions divided here. A quotient is associated with that division process, so the quotient function is u of x on v of x. If we multiply across by v of x, we would have u of x equal to q of x by v of x. Oh, it's a product now. So we can get at the quotient rule, not from first principles, but by using the product rule. Okay, so the derivative of the left-hand side is u dash x. Let's use the product rule here. Derivative of the first by the second unchanged, plus the first unchanged derivative of the second. This derivation comes from Hayes, and Harris, and they line up more with what I like, and that is, remember, derivative of the first by the second unchanged plus first unchanged by derivative of the second. Okay, in that order. Okay, so if we want to try and get q dash x, which was the derivative of our original function up here, let's move this term across the other side, subtract it, and then what do we have? They've rewritten it on the left, is that, and replacing q of x with u of x on v of x, then dividing through by v of x, and getting it all over v of x, then common denominator, this would be u dashed x by v of x on v of x gave u dashed x, just having a common denominator there, and then dividing through. So you've got a division there by v of x all squared. Well, that's a mess, isn't it? That's quite complicated. Okay, so we have to remember that. Can you see that if you've remembered the product rule like this, the quotient rule, which has got a negative, so you've got to watch which term goes first with the quotient rule. Can you see the top line is almost the same? Let's look at it. Derivative of the first by the second unchanged, minus though the first unchanged by the derivative of the second, all over, the second function I'm calling the denominator, all over the denominator squared. So the top lines are the same pattern, one's got a negative. So that makes it easier to sort of remember the formula rather than have to copy down from the formula book. That pattern is the same, just with a negative in front. So that's why I like to think of both of them this way rather than have to change it around. Okay, between the product and the quotient rule. You'll get the hang of it as we go. Let's have a look then. Here we have it. If it's a quotient, then derivative of the first by the second unchanged minus, so this is the difference between this one and the product, the first unchanged by derivative of the second, all over the denominator squared, or the second function squared. Okay, u of x and v of x, thinking about first being the top one and second function being the bottom one, numerator denominator if you like. And that there's a neater way without the x of stating it. Okay, let's apply it and get the hang of this. Okay, so example 10 from Pearson's. Look at this. I think we can finally do the tangent, find the derivative and find why it has that interesting graph that we had a look at briefly in the last presentation. Because the tangent is a quotient, sine divided by cos, from way back at the beginning of this course. Okay, so there's our two functions. Let's use the derivative of the quotient rule here. So it's the first unchanged. Derivative of the first by the second unchanged, derivative of sine is cos, minus first unchanged, watch this, derivative of cos is sine, but that's a problem one, remember I told you, that's negative. So this is the derivative of cos x. Just remember cos x is a bit problematic with the derivative, because its derivative is sine, sure, but it's neg sine. whereas the derivative of sine is just straight cos. Remember, cos is the one you've got to have a negative in front. So then we have cos squared plus sine squared on cos squared. Oh, interesting. Negative times a negative. And you know that that is 1. Sine squared plus cos squared is 1. That's one of those trig identities, the circular function identities there. So it's 1 over cos squared. And that's sometimes called sec squared, sec standing for secant. 1 on cos is the sec of x, but we don't need to know that in this course. And if you then draw the graph as I showed you in the last presentation, you get this thing. And you can also check that by graphing the derivative of tan x, as we did back earlier in an earlier presentation. Alright, so we can actually prove the derivative of tan x is 1 on cos squared, and it's got that interesting function. And as Pearson's have mentioned down here, that completes our set of rules for the trig functions. We've got sine, cos and tan. That's all we have in this course. Okay, let's go on and use it in another example. First of all, we'll just summarise that. You are expected to know, although this is in the formula booklet, that if you have a function tan x, its derivative is 1 on cos squared. Alright, very good. Let's go down. Here we have example 11. We've got 1 on 2x take 3. Find the derivative by the quotient rule and the chain rule. Well, generally we don't do this. This is not really a quotient, it's a constant, isn't it? It will work. Okay, derivative of the top line is 0, by bottom line unchanged. And now I don't know why they don't put that first, f in front of g, f dash x, g of x. But anyway, and then in the second one here, first function unchanged derivative of the second over the square. So here this goes out, and it's just negative 2 over 2x take 3 squared. Generally you do not use the quotient rule if you have some constant, well let's call it c on top there. C on some function in x, because c is a constant. Okay, so we generally wouldn't use the quotient rule for that. We would do it this way. And that is 1 on 2x take 3 is 2x take 3 to the neg 1, which is therefore just come down using the chain rule. It's neg 2x take 3 to the neg 2. That's doing that outside function, if you like, the neg 1 power here, become neg 2x take 3 to the neg 2 x to the n rule, and then the derivative of what's inside the bracket, that second function, giving us a 2. It's a chain of derivatives therefore. Okay, and we can reconstitute it back like that. Okay, you can apply other rules other than the quotient rule if it's simpler, and here the chain rule is simpler because we don't really have a quotient of two functions as such. Okay, example 12, here we go. Some more just to have a look at before we go into chance for you to practice. Here's the first one. Second one, let's go and do the pieces. So derivative of the first function is 3 by the denominator of second function unchanged, then the top line unchanged by the derivative of the bottom, all over the bottom squared. Okay, and you can go through and expand that. Now this is something I don't really want you to do. Pearson's are showing it for completeness here. You can make the function a product, right, by saying the top line by the bottom line to the neg 1. Okay, so you can do that, but generally we wouldn't. We've got 3x take 2 then by the derivative of the second term, and then the derivative here of the first term by the second unchanged. So using that rule again, and this time that's a functional chain rule. So there's its derivative, and then we just go on. And you've got to put it back together again at the end into this form. Okay, so there's a fair bit of work there. Generally use the quotient rule if it is a quotient of two functions. generally do not convert to a product. Generally it's more work. Back to a product, because you get a -1 and that's going to mean you're using the chain rule. It gets a bit messy anyway. Right, let's look at the other one that they had up there. 5x take 1 on 3x squared. Okay, so derivative of the top function by the bottom one unchanged minus top function unchanged by derivative of the bottom. Okay, just check that. Derivative of the top is 5. Derivative of the bottom is 6x. Yep. Okay, so then you can just simplify it. Generally, in a lot of work, if we're not going on to find the equation of a tangent or something, you do not simplify your answer so that the marker can actually see the parts of the derivative that you constructed there. But we can expand all that and collect terms and get our answer. Now here's an interesting variation for this one. Do you want to look at this? You could call that 5x on 3x squared, take 1 on 3x squared, and bring it all down to x to the ends, rather than use the quotient rule, and then just do it term by term. Derivative of this is -5 over 3x to the -2. Derivative of this is -1/3, and the derivative of this part -2x to the -3. So we're using the x to the n or power rule here. So that might be actually easier than using the quotient rule. Now you can only do that if you can split the top line. You can split the numerator, but you can't split the denominator. You can't, for example, do anything with that. You cannot split that up. It means 3x squared divided by all of 5x take 1. You cannot split any denominators. So down here they've done a bit of algebra to show that the two methods are the same. So keep your wits about you now, because you have got options for finding the derivative of more complicated functions. Okay, let's go down to here. We just covered that, I think. That function looks similar. It's reciprocal, but you actually can't split it. You cannot do that, because 3x squared over 5x take 1 means 3x squared divided by all of 5x take 1, and that is not divide by 5x and then take 3x squared divided by 1. Okay, so we would use the quotient rule there, and generally we don't change it to that product. Generally the quotient rule is the best way to go, even if we're going to work further with the derivative. Alright, so do not split bottom lines or denominators. You can't do that. Okay, that is not the meaning of that expression. Okay, let's have a look at your having a go there, you having a go. And before we do that, I just want to bring up, this is from the formula booklet from the IB. Okay, that they give you in exams. So you've got the first principles, x to the n rule, derivative of sine is cos, derivative of cos is minus sine. Remember, cos is problematic there. Got to remember to stick its minus in there, negative sign. Derivative of tan, 1 on cos squared. Derivative of e is itself. Derivative of ln x is 1 on x. This is just a summary of all the basic types of functions. Here's the chain rule. We've got two functions. Derivative of the first, then derivative of the second, outside, inside functions if you want to use Pearson's notation. Remember, we've got to spot the functions. Spot the functions involved to use this chain rule or function of a function rule. Okay, derivative of a product. Here it is, the wrong way around, because if we put this one first, the derivative of the first function, I want to put this first. du by dv by v plus here u by dv by dx. So they are the same, but putting it in that form, can you see then it's the same order of terms as this one? So you get the derivative of the first function, second unchanged, plus first function unchanged derivative of the second, and then when you go to quotient, all you've got to do is change that to a negative. Okay, rather than these look quite different. Put like this, you're juggling the terms around. So there's no reason why you can't here put that in front so it mates up with this one, if you like. Okay. Alright, so up to you. You will be given that in your formula book. That is a clipping from the formula book for differential calculus section. Okay, are you ready? You might have to look back at some of those to be able to do the problems now. Let's have a look at the problems. So the first two, again, coming up below now are the solutions, fully worked solutions from Pearson. So as you do one, scroll forward, have a look, mark it and come back. You need to do all of these. There are only 6 questions here. There's question 1 and 2, so pause the presentation and have a go. Let's have a look at question 3. And we've got 3, 4 and 5 in there at least there. Now this means we're going to actually use the quotient rule and go on and find stationary points and things. We've got to be able to do that using the applications of the derivative. Okay, let's go to number 6. I think number 6 is the last one. Okay, so there's number 6. Alright, so what we'll do now is have a look at the solutions just slowly and check them out. Okay, so that's question 1 through to J. Check the lines of calculation there. Work down the page, not across, like Pearson's have done here. That's doing that to save room. Okay, let's go on. We'll just go down to K, we didn't see all of K. And question 2, down to B. Okay, and C. Let's see if we can get a bit more in. Okay, and see if we can get the rest of 3. Almost. Big question 3. Lots happening there. Rest of E in 3. Okay, and question 4. 4, 5. We'll get the rest of 5 in a minute. There's a graph for 5. And 6. And there we have it. So some of the numbers there are getting fairly difficult to work with. Some of the fractions, you've got to keep your wits about you there. All right. I hope you're pretty proud of yourself with how far you've come now, and that's almost at the end of differential calculus. So you can do a lot of differentiation now, can't you? And we've got one little section left on a further application. So I look forward to presenting that to you shortly, but for now, cheers from me.